Hello everyone, welcome. I'm Yash. I work for the photos team at Google. And today I'll be talking about how do you identify barriers of latency in your microservice systems and strategies to basically mitigate these. So back to the basics. So when you look at monoliths, you have one big application performing the entire request response flow. But in microservices, there are several smaller services talking to each other, and each of them being independent, lightweight, and most importantly, reusable across different workflows. So the critical observation here is the large number of network calls. And as you can imagine, the performance of the system directly depends on how optimized these network calls actually are. So you definitely do not want to have something like this, where even for a single flow, your applications have to basically interact across some kind of network barrier with high latency involved. And in terms of the barriers, what I'm talking about is something like maybe the obvious ones, which are geographical regions, zones, and data center. But other than that, there are a lot of other highly prudent but invisible barriers available as well. So for example, you have firewalls, maybe CDNs, sometimes you have gateways, protocols. A lot of them basically are hard to account for but do impact performance. In fact, in one of my previous firms, I remember there was a situation where we had, basically the security team has flagged some of the sources which were kind of higher security risk, so we had to make them go through another round of auth Z and auth N. So that was another kind of a network barrier which we generally don't see, but it does impact the services a lot. So to avoid them, basically the general principle is to keep the applications closed. It could be either in terms of placement, where you try to keep all your applications within a single, that barrier we're talking about. Or the other option is basically to replicate. You have all the services running in all the possible barriers, which of course is costly, but that is an option that you potentially have to do at the end of the day. Now, this looks simple to solve, but it really is not. First of all, you have to understand each and every applications, what are involved in the flows. There could be hundreds of services, thousands of workflows, complicated as well. And most importantly, these things can change fast. They're not dynamic. And unless you're an architect or owner or you know each and everything in and out, it's a little difficult to get a hang of it, or it at least takes a lot of time. And same goes with the infrastructure as well. You don't know which nodes are closed, what kind of barriers exist, and it's all in all a little difficult thing to get a hang of once the scale is beyond a certain amount. So what we need is a way to basically understand which services to replicate and where to replicate, and basically you want to at the same time try to reduce costs as well. So let's solve together. The first step, what we'll do is basically understand the applications and the workflows we have. So one way to do that is basically simply monitor the network spans that you have in the system by using the network. For example, one way is to go through the host OS, see the network logs, resolve from pod IP to service FQDNs and understand the span. And that can help you basically get a graph of this sort where you can understand what the applications and how they're interacting. The next step basically is to append this graph which we just found with the latency info. We can leverage the same logs, basically keep a delta of what the timings of source and destination were, and we get the time which was spent in the interaction itself. Now, one thing to observe is that this is very bare bone, does not involve any sidecar, any setup, no service mesh, no third-party monitoring tools, and we're doing this out of the box ourselves. But you probably don't need to reinvent the wheel here. You can leverage tools like OpenTelemetry along with a backend like Grafana and maybe Prometheus to get this at scale. You can do something like maybe have your application instrumented and have client-server spans added as a metric, and you can persist them and do a custom query to basically figure out a delta. And there are some other options and patterns using Jaeger and closed source solutions as well to get this out of the box. The interesting part is basically how you get to figure out the network barriers. So we do have the latency info, which we build upon now. We roll this data up by nodes and basically keep a running average. This tells the historical running average of what the latency has been when pods across different types have been running on these nodes, interacting with the other node that is there. And once we have this, the last stage is basically to group the nodes which are closed and which are not. So it simply becomes like a graph problem, where you have nodes as actual nodes, and the edges are the average latency that we just found. So it's all about clustering the nodes, and you can use any of the existing several algorithms we have. One simple non-compute intensive approach that we use for the greedy one, where you start with one node, keep adding the nodes which are nearby to it as long as the weight of the edges are lower than what we already have found till now. So in this example, you do it starting for all those basically all those nodes, and you figure out all those potential network node groups. And once we have these potential options, what you do is we need to figure out which one to choose. So one mathematical construct that can help us is called something called latency ratio, where it's the sum of latencies which are internally versus what are external. So you want this ratio to be as minimal as possible because you want low latency within all the nodes which you're going to be grouping. And once you have this, we select the overall set of groups that captures all the nodes, and basically it has the least number that you can find here. So in the example that we just have, we find something like this, where we have 3 groups here with these nodes. But what it represents is basically a sufficient number of node groups where replicas are needed. In this example, instead of at max 8 replicas of all the services, you probably don't need to do that. You only need 3 at max. And this is more than sufficient and probably will suffice for any. I don't need to basically optimize any more than that. And one final thing you can probably ask is, what if I cannot replicate? In a lot of cases, first of all, replication is complicated. But more than that, sometimes you cannot replicate, because sometimes you have compliance regulations, data cannot even go out of a certain set of nodes, or even other than that, in flight as well. So can something be done instead of replication? Maybe some kind of a trade-off where we can do something interesting other than just simply blindly replicating. So actually we can. Let's take an example here where we have 3 distinct network groups and interactions are like this. So if you observe closely, in this case, we also have the volume of calls over, let's say, an hour. So in this case, instead of replicating the application C in both of these other clusters as well, you can actually migrate this on just the first node group, and you can still save a lot of network latency in aggregate because you have a lot more volume of calls coming from that particular node group. This is despite the increased latency that is there between node group 1 and 3, which is 150 milliseconds on average, but the volume offsets that. So coming back to our previous solution, to do something like this, what we do is we already have the historical latency. We basically append the interaction counts, and this is basically an average volume of calls across a given time frame. And once we have this, we can basically get some kind of a smart recommendation like this, where we get, instead of basically replicating, what you get is a recommendation where something like, maybe migrate from group 1 to one of the 3 nodes you have here. You can save so and so amount of cost, and maybe you'll still basically speed up your system by a certain amount of time. And of course, this is just not for one span, it's basically across aggregate or for a particular amount of time. So it basically helps in aggregate and not just one. And how we actually did employ this last one in one of our test environments, where we had a setup of nodes across different data centers and regions, and even across different geo regions as well. And we did a consolidated optimization, and we tried to save cost and performance both. So we observed around 5% of savings in monthly infra costs, around $230 or something. But the important thing here is that the fact that this was done without any kind of impact in any latency of any kind. There was no perceivable difference in any performance of any other of the existing network calls, as well as any in the system, any pods, any container whatsoever. And this tells us how much of a important thing this is. You don't really need to replicate blindly. These kind of optimizations are not so visible, but can help you save a lot. So that's all about it. I don't really have a time for a Q&A, but if you do have any questions, just reach out to me and I'll be happy to answer them. Thank you so much.